In this lesson, we will be outlining the basic steps that we will see in most of our mechanisms. Understanding these individual steps will help us to understand the patterns of reaction mechanisms we see throughout the rest of this class. Many of these reactions are in the form of a Lewis acid and a Lewis base reaction. Many reactions fall into this category, including the Bronsted-Lowry acids and bases we talked about last chapter. A Lewis base is an electron pair donor, which will take its electrons to form new bonds with a Lewis acid, electron pair recipient. Because the electrons from a Lewis base like to interact with positively charged nuclei, we refer to Lewis bases as nucleophiles in much of organic chemistry. Likewise, the recipients of electrons in these reactions are electron poor and want more electrons, and we refer to these Lewis acids as electrophiles in much of organic chemistry. Two things to note about these reactions in particular. First, the nucleophiles are electron-rich and are either formally negative or negative from a dipole, and the electrophiles are electron-poor and are either formally positive or positive from a dipole. Opposites attract. Second, if we form a new bond to an atom that already has a full octet, something else has to go. We can't have more than a duet for hydrogen and more than an octet for carbon and other second period atoms. Now let's talk a little bit more about our nucleophiles. Some of our best Lewis bases or nucleophiles are charged species, but we can never add just one ion. We have to add it with a counter ion. We're always going to add a full ionic compound. Some of our cations are able to balance the charge on a nucleophile or base, but are so stable as cations that they're practically inert, and we call them spectator ions, since they just watch the actual reaction. Great examples of these are lithium, sodium, potassium, and even magnesium +2 in most cases. These ions are generally ignored when they show up, but they can be really great ways of stabilizing negative charge on atoms that are highly reactive, like carbanions. Some examples include alkyl lithium reagents, so that's a carbon attached to a lithium, or Grignard reagents, which would be a carbon attached to a magnesium, or Gilman reagents, which would be a carbon attached to a copper, which is then stabilized by a lithium. Each of these carbons is attached to a metal, meaning that the carbon is going to be more electronegative than the metal and will be negative. Because the metal is ignored, we often think about the reactivity as the carbanion alone, the negatively charged carbon alone, like we can see to the right. Spectator ions allow us to access these really powerful nucleophiles. Spectator ions can stabilize other anions too. For example, we can stabilize hydrides, negatively charged hydrogens, as aluminum or borohydrides with a group 1 spectator ion. So in addition to the electronegative atoms that normally can stabilize charge, if we use a metal for stabilization, we could also generate carbon and hydrogen-based nucleophiles. These become really important for forming bonds that are otherwise pretty difficult to form. One of the most important reactions in organic chemistry is the nucleophilic substitution reaction, where we're able to replace one group with another group. When this happens all at once, we say that it is a bimolecular nucleophilic substitution reaction, and we abbreviate it SN2. Bimolecular, since two reactions are involved, that gives us the 2, N for nucleophilic and S for substitution. In this type of reaction, we necessarily need a leaving group as well as a nucleophile, because we cannot exceed a full valence on the atom being substituted. So a leaving group needs to leave in order to make room for the nucleophile to come in. Since the leaving group needs to be somewhat stable on its own, they are usually best when they are the conjugate bases of strong acids. Remember from last chapter that these acids are usually strong in the first place because they can stabilize the charge left behind. Our nucleophiles are Lewis bases, meaning they have a lone pair that can form a bond. They always have some negative character because they are attracted to the positively charged electrophile. The nucleophile will come in and attack the electrophile, which at the same time will release the leaving group. If nucleophilic substitution takes place in 2 steps instead of 1, the first step is always a heterolysis. Heterolysis is where we break a bond unevenly, resulting in the more electronegative atom becoming an anion and the less electronegative atom becoming a cation. You can kind of think of this as a leaving group leaving. The entire two-step substitution process is called a unimolecular nucleophilic substitution because the first step only involves one molecule, unimolecular. Heterolysis always needs to happen first in a unimolecular nucleophilic substitution because if a nucleophile added before the leaving group left, before the heterolysis, the electrophile's valence would be exceeded. Heterolysis steps are the most likely to occur when there are factors that stabilize the charge of the products, or no increase in charge between the reactants and products at all, like in the second heterolysis reaction that's shown. The second step in a unimolecular nucleophilic substitution reaction is a coordination step. Coordination is the exact reverse of heterolysis. This is again a simple Lewis acid-Lewis base reaction. A nucleophile donates electrons to an electrophile. Because these coordinations are complete steps all on their own, the Lewis acid must have an incomplete valence, meaning coordinations tend to yield products that have lower energy since their valences are now complete. This is true for coordinations that happen independent of unimolecular nucleophilic substitutions as well. Another reaction that takes place with a concerted, meaning all at once, mechanism is the bimolecular elimination reaction, which we designate as E2. Remember from chapter 6 that hydrogens attached to sp3 carbons are not particularly acidic. Here, the hydrogens are more acidic because the negative charge of the conjugate base is immediately stabilized in a pi bond by kicking out a leaving group. For this elimination to occur, we generally need a strong base and a leaving group that will be fairly stable as an anion. A generalized mechanism is shown. The base pulls off a hydrogen, and the electrons from that bond form a pi bond to an adjacent carbon with a leaving group. Notice that there always needs to be a leaving group that is kicked off, and the hydrogen that reacts is always just one carbon away. Sometimes there is no leaving group, but a nucleophile may still add by kicking pi electrons out of a multiple bond onto a neighboring electronegative atom. These nucleophilic addition reactions are fairly common, particularly on carbonyl-containing compounds and their nitrogen analogs, since oxygen and nitrogen both can stabilize negative charges reasonably well. It will always be a nucleophile that attacks the carbons in these bonds, since the carbons are the place that holds the partial positive charge. The nucleophiles can easily be nitrogen or oxygen based, and in these cases are often reversible. If the nucleophile in an addition reaction is a carbon-based nucleophile, like in a Grignard reagent, or carbanion that's attached to a magnesium bromide, the reaction will be functionally irreversible, since it's very difficult to stabilize a carbanion better than having it bound to another carbon. Similarly, hydrides react in a way that is functionally irreversible via nucleophilic additions. The generalized reaction that's shown shows a nucleophile replacing a pi bond, which could be from either a double bond or from a triple bond. Both are equally viable. Nucleophilic elimination is the reverse of nucleophilic addition, where electrons on an attached electronegative atom, usually nitrogen or oxygen, are used to create a new pi bond that eliminates a leaving group. The leaving group that was eliminated is now significantly more nucleophilic, since it left with its electrons. The generalized mechanism looks like this, where some electronegative atom moves its electrons into a pi bond, where at the same time a leaving group takes its electrons and runs. When carbons are double bound to each other, rather than to a nitrogen or an oxygen, neither carbon carries a positive charge. In fact, due to the extra electron density that's held in pi bonds, alkenes, alkynes, and even aromatics can react as nucleophiles, attacking positively charged electrophiles, as shown below. In each of these examples, after we attack a positive charge, a carbocation is left behind, and that carbocation is the same no matter where we've attached the positively charged piece. In most reactions, the positive charge after attacking an electrophile could end up on either of the carbons from the multiple bond, but one will be drastically more stable and therefore drastically preferred. We'll talk more about this in chapter 11 and 12, but for now, we assume that we attack an electron-poor electrophile with a double bond from an alkene or an alkyne, and we end up with a positively charged carbocation. The opposite of an electrophilic addition is an electrophilic elimination, where a positively charged electrophile gets kicked out to form a double bond. Commonly, this positively charged electrophile is a proton. This is the second step of a unimolecular elimination reaction, where the first step is a heterolysis step. Because one reactant is already charged, it is common for us to be able to accomplish this type of reaction with a relatively weak base to stabilize the eliminated electrophile. Our last type of reaction is the 1,2 shift. Since many of our elementary steps may result in the formation of a carbocation with an incomplete valence, neighboring sigma bonds will lean into the empty p orbital slightly and stabilize the incomplete valence. As these bonds lean in, they can actually hop over to the carbocation, taking their electrons with them to the new location. This really only occurs if the carbocation left behind will be more stable than the one disappearing, which usually means that the carbocation will be more substituted. 1,2 shifts can be a shift of a hydride, a 1,2 hydride shift, or they can be a chain of carbons, a 1,2 alkyl shift. Remember from our discussions in chapter 6 that reactions tend to be favorable when there is greater stabilization of charges, that is, more complete octets and greater total bond energy. The first reaction shows a highly favorable coordination step, where the octet is completed and 2 formal charges are eliminated. The second reaction shows a fluorine, which can stabilize a negative charge somewhat, replacing a chlorine, which is larger and can better stabilize the negative charge. For this reason, fluorine has a stronger bond to hydrogen, and for the same reason, the reaction is favored. These factors can help us decide whether reactions are likely to occur and to what extent, but they don't necessarily tell us how fast the reaction will occur. We talk a lot about charge stabilization, but sometimes the less stable structure is actually the one that dictates product formation, especially in situations where equilibrium is at play. Of the 2 resonance structures for the enolate that are shown on the left, the top has the negative charge on the oxygen, which is much more stable. However, the bottom product, the keto form, has an overall greater stabilization from its bonding pattern and is greatly favored. The products aren't permanent though in this reaction, and the keto and enol form are generally both present in some amount, but drastically favoring the keto form. The relationship between these 2 products, isomers, is special. We call them tautomers. The reaction that is needed to interconvert these tautomers is called tautomerization. Keto-enol tautomerization makes a surprise guest appearance in glycolysis, as well as many other places. Glucose 6-phosphate is formed by hexokinase when a glucose molecule enters a cell, but it needs to be tautomerized to the enol and then back out into the ketone in order to continue the process of glycolysis. What a world!